Okay, so for the Cal 2 class, let's talk about 9.3. That's the homework. I have it up there to save a little time. Pick 5 of them, and then I'll ask to see your notebook at the end of the semester. So 9.3 is basically introducing 2 tests, okay? We've got the integral test and the p-series, okay? Now the integral test, okay, says, first of all, we need a continuous function that is equal to the points, right? The discrete points of this sequence, a sub n, for all n, okay? So given that we have this function, okay, if this function is positive, it has to be decreasing, okay, and it has to be continuous. Now, these 3 things have to be verified: positive, decreasing, and continuous, okay? So if this is all true, right, and if this integral from some constant here, okay, of the function, if this thing converges, okay, that implies that this converges, okay? And if it diverges, that implies that this thing diverges, right? Notice that that's not always the case with these tests, right? Sometimes it'll prove that it converges, but it won't prove that it diverges if the test doesn't come out the way you want it. So this one, pretty definitive, all right? So an example problem that you could use the integral test for, okay, would be this one right here. This is number 79 in the book, okay? And it is 1 over n log n cubed, okay? So the function that we would use would be 1 over x log x cubed, okay? So, you know, is it positive? Oh, and this thing starts here at 2, okay? And it doesn't matter where the series starts. Just, the first finite number of terms don't affect the convergence or divergence of the series. It's just the end behavior. So from 2 up, log x is increasing, x is increasing, so the product, the cube is increasing. This is definitely increasing. It's a fraction, so this function is decreasing, okay? 1 over x is continuous for x larger than 2. Log x is continuous, x larger than 2. So we've got that it's continuous. And it's positive, again, log x is positive, and x is positive for x larger than 2. So it meets all the criteria, okay? And so we would want to try the integral, right? So we're going to start here at 2, take this thing to infinity, and we probably want to rewrite this as log x to the negative 3, 1 over x dx, right? Because here we've got the integral from 2 to infinity of u to the negative 3 du. So this would be the limit as b approaches infinity, right, of what? 1 over 2 log x squared. This would be negative. And we're going to take this from 2 to b. So if this thing converges, then we know that the series converges. If it diverges, we know it diverges. Notice that when you plug in 2 here, you know, you get a number. And remember, we don't really care what the value of this limit is. All we care about is that it exists. When we plug, you know, the b in and take the limit, notice that this bottom of this fraction is going to go to infinity. That's going to be 0. So this thing is definitely going to exist, okay? This is going to converge, and that shows us that this series also converges, okay? The other thing that's covered in here is the p-series, okay? The p-series looks like this. P is the exponent, okay? And if p is between, it can be less than or equal to 1, then this thing is going to diverge, okay? And if p is greater than 1, then it will converge, okay? So these are pretty straightforward. Look at a few examples in the book. You know, basically 1 over n, where The exponent is 1, p is 1, diverges, that's a harmonic series, that's a divergent series, 1 over n squared, that's a convergent p series. All right? Notice that these things both pass the nth term test, right? The nth term test, the limit is 0. So the nth term test is a test for divergence, not for convergence. If you have any questions about any of these, send me an email, and I'll try to make a video to answer.